Hi, this is Mike Tochik. I'm with Dairyland Electrical Industries, and let's talk today about more misunderstandings regarding overvoltage protection. I'd given a previous presentation on misunderstandings that can come up regarding overvoltage protection in general, and you may want to reference that other presentation as well. It gives a number of basic topics. And there's enough of them that it warranted having an additional presentation just to cover the balance. In the past, we covered 10 different topics that come up very commonly, enough so that we just had to talk about them. The following are true statements, and we'd like to review those just very briefly, and the other presentations available to look at these in depth. First, gradient control mats really aren't very good AC mitigation grounds. People think of those as grounding mats equal good grounding, but these are really there for step and touch voltage protection for workers. They work very good at that function, but they aren't low resistance grounds. Second, conductor length matters in dealing with lightning for overvoltage protection. And there's ways that one can apply and use techniques to employ limited conductor length in order to limit lightning overvoltage. Now, back to gradient control mats, not every design actually provides overvoltage protection specifically for lightning. You'd be astounded at how different the performance can be between different mats. Further topics. Sometimes conductor length isn't the key issue for all applications. One can think of this as being a practice to be followed in all situations, but there are some applications, such as a code-covered grounding conductor, that just can't be shortened if it's running from a panel to an electrical device. Next, electrical isolation of structures can be risky if there's no overvoltage protection provided. So sometimes structures are left mechanically isolated one from another using insulated joints, but users have provided no overvoltage protection, and they just somehow think that magically this structure will remain isolated forever from the other structure. However, then it means it can rise in voltage to any level. There's no means of protection. Sometimes people think of decouplers as one-way devices, like a diode. Well, decouplers always are two-way devices. They will limit voltage in either polarity, and so there are some misunderstandings there that come up. Interesting topic. Finally, AC induction always has a fault risk. One can think of the steady state effects that they could experience on a pipeline, but then minimize or forget about fault conditions. And those are always present because the same induction that brings steady state conditions also can bring fault risks. And a couple of more. Lightning is not the same type of signal as AC or DC. It has to be treated differently because it's a very different waveform and it produces different effects. Regarding insulated joints, some think of monolithic joints as the ultimate protection, and they are very good insulation systems, but they will fail if you provide enough voltage across that joint insulation. So they need protection as well. And last topic discussed in the previous presentation would be that equipment grounds have to be left in place for safety. You cannot sever an equipment ground just because it's a nuisance for your cathodic protection system. It really must be left in place. Instead, there are decouplers that are UL listed to be placed in series in grounds to solve these kinds of problems. And now for the new topics. Let's talk about these 5 today. First, let's compare the NACE 15-volt criteria to a discussion about AC corrosion and the voltages that relate to that. Next, we'll talk back to lightning again, and this time we'll tackle the subject of wire straightness. We hear a lot of comments about wires needing to be straight, and I'd like to get into the specifics of that. On isolation and attempts to protect electronics, sometimes people will leave their electronics electrically isolated in order to not have them fail. There are some problems with doing so, however. Similarly, with rectifiers, There's various rectifier protection schemes that are out there. Some of them will work and some miss the boat. And finally, let's say that you've mitigated AC or are attempting to mitigate AC, but you're unhappy with the voltage on the pipe. Why would it still be too high? Does the system not work? First, we'll tackle the NACE 15-volt criteria and the relationship between that and AC corrosion. The document NACE SP0177 is a very useful document that I'd recommend you obtain from NACE.org, and it references 15-volt criteria, which is safety criteria. The whole document relates to safety issues for pipeline personnel and the conditions that they might be exposed to. There's a section in there, an example of it shown here, where it's talking about safety and personnel and shock hazards. And note, it's talking about a steady state voltage of 15 volts. Well, if steady state is 15 volts, just keep in mind, under fault conditions, voltages on pipelines can go much higher. And all of these are discussions about safety hazards for personnel. There's no discussion in here about AC corrosion at all. Sticking to the safety topic, though, for a moment before we switch over to AC corrosion, these standards have developed the 15-volt criteria as a relationship of typical personnel resistance, skin resistance, or resistance to earth, and the maximum current that a person could be exposed to safely and attempt to survive that event. And so these values of 15 milliamps and roughly 1,000 ohms yield about a 15-volt limit for safety, but understand that some personnel could be affected by currents less than 15 milliamps and may have a resistance that is represented as less than 1,000 ohms. So the total resulting voltage that still could be a hazard could be less than 15 volts. However, the industry still uses this as a basic criteria. Now, AC corrosion and the associated voltage that produces that corrosion is quite unrelated to safety. Once you've mitigated for AC or attempted to mitigate, that is for safety, and that level that you've mitigated to for voltage on the pipe may not be adequate to address AC corrosion, and AC corrosion could still occur. So mitigation in itself is not the answer to all things. The mitigation level, the resulting voltage specifically, must be low enough to prevent AC corrosion under certain conditions, or else it could occur at defects in the coating. Here's a useful graph that can show quite a bit of information. We have AC voltage on the vertical axis graphed against soil resistivity on the horizontal. You'll notice that at 15 volts, you'll see the horizontal line with the yellow dashes representing the NACE 15-volt criteria. You'll also see some brightly colored lines crossing this graph, and that is current density shown in amps per square meter with some typical industry agreed criteria shown on there. The pink line on the bottom represents a current density of 20 amps per square meter up through the green line, which is a higher current density of 100 amps per square meter. And those are generally given as the lower and upper limits to current density awareness or warnings to the industry. Below 20 amps per square meter, AC corrosion is generally considered not to occur, and the risk increases, and by 100 amps per square meter, it's generally agreed that AC corrosion is a higher risk. Certainly, current densities could get above these values, and they'd represent higher risks yet. So looking at this graph, let's examine a situation where you might have limited soil resistivity, say several thousand ohm centimeter soil. And if you were to find that on the horizontal axis and now trace that line upwards until you hit the 100 amp per square meter line, the green line, and now translate over to the left, you would see that perhaps you might have 5 volts of induced voltage on the pipe in 1,000 ohm centimeter soil roughly would produce 100 amps per square meter of current density, a value that's considered to be unacceptably high. Most people may not mitigate AC for safety down to 5 volts. They might be attempting to mitigate only down to below 15 volts. You can see that this difference yields a gap where the pipeline is at risk. It might not be for safety, but for AC corrosion, it may not be protected. So, in conclusion, AC corrosion can occur at levels well below 15 volts. It can occur at even only several volts. So you have to look at the AC voltage on the pipe, even after mitigation, and the soil resistivity. The key here is it's the low soil resistivity areas that are the concern, and they will have the corrosion risk. You're not going to have a problem with high soil resistivity areas. So if you must concentrate your efforts and your maintenance dollars somewhere, focus on the low resistivity areas. The result will be, if you put in additional mitigation grounding, that would reduce the induced voltage further. Let's switch topics to lightning and the concept of wire straightness. The term straightness comes up a lot, or the discussion about straight wires is a very frequent one. Is that related? Is it actually true that straight wires would limit overvoltage? And we see specs that say don't have any bends in your wire. Well, it's partly correct. There's several things that lead to overvoltage conditions for lightning. One is the waveform shape, another is the length of wire involved, and also the orientation of the wire. So we'll relate that to our straightness discussion. Well, the waveform involved that can produce overvoltages could be things like lightning or fault current. But only lightning is going to produce a high voltage that relates to cable length. AC faults, the main concern there is the wire ampacity, the wire size, so that it can withstand the energy of the event. But for lightning, it's all about length. Lightning has a very fast rise time, and AC waveforms do not. And it's this fast rise time that produces the effects that we're concerned about. If there's increased length of the wire, that involves greater inductance. And inductance is an electrical property that resists rapid changes in current levels. If for some reason there is a large current change for current flowing in the wire, it will result in a high voltage being produced, a very rapid large voltage. Now back to orientation. Here's a comparison of the number of turns in a wire and the resulting inductance, which leads to the voltage effects we're talking about. Note the difference between 1 turn of a wire, 2 turns, and 4 turns. You'll see that there's an exponential effect on inductance and therefore voltage for adding turns of wire. So we've shown this graph relative to 1 turn, but clearly these turns are detrimental in the sense of limiting voltage. These turns are useful if you consider other electrical properties of making a coil for an intended purpose. You're using the property of inductance to accomplish another effect. Here we're trying to limit voltage between 2 points. We don't want extra turns, and we don't want extra length. You could discuss this as a point of straightness, but really we want to limit length in order to limit voltage. So avoid turns and avoid extra length in cables. Electronics and their failures can be associated at times for users with lightning events and AC fault events. Sometimes in order to deal with that, users might think of leaving their electronics to float electrically and not bond them to certain structures in an attempt to isolate them from harmful effects on those structures, say a pipeline. That usually means let's not bond it or ground it to something else. The problem is devices that are not bonded or referenced to other structures can rise in voltage beyond the voltage withstand of the insulation system or the insulation of the wires and eventually failing electronic components or the like. The solution is to reference electrical equipment or devices to ground or to other structures with an appropriate overvoltage protection device. We don't want to let the electrical equipment float and rise to a very high voltage where it could possibly fail. So think of as an example a transducer on a pipeline. If the transducer or its shield were isolated and that isolation point were left open with no further protection, the pipeline could rise in voltage and fail the transducer. So bonding across with an appropriate overvoltage protection device would alleviate that. Similar to equipment protection discussions, let's get more specific to rectifiers. Rectifiers are used for cathodic protection on pipelines and other structures, and in that application, they're exposed to quite the electrical elements, and they can often fail due to lightning conditions, or it could be fault conditions as well, but they generally need overvoltage protection. So commonly, arresters are used in the output terminals of the rectifier, and clearly they're meant to address, an attempt to address at least, the failure conditions. But rectifiers still fail, so obviously something is being missed. Well, overvoltage protection on rectifiers is needed for the reverse polarity on the diode stack. If the diodes in the stack had a opposite polarity of a high magnitude applied to them, that's where you can fail the diode electrically, and that would be the end of the rectifier. So overvoltage protection is needed for that reverse direction. One thing that's often forgotten is that in the forward bias direction for rectifiers and diodes, the issue isn't reverse voltage, it's already in conduction. It's overcurrent. So when the forward bias diode has current beyond what it's rated, it could also fail. So overvoltage protection is limiting the voltage on the output of the rectifier to deal with the reverse polarity, and we use metal oxide varistors or arresters, spark gap arresters, something like that. For overcurrent protection, this one's a little trickier, but sometimes various methods involving coils, which actually is using inductance to accomplish something useful, to limit current, that has been done, say on the negative lead of the rectifier. In fact, Dairyland at one time produced a rectifier protector product that did this very function of protecting overcurrent and overvoltage for rectifiers. Sometimes customers ask if a decoupler, a Dairyland decoupler, could be connected across the rectifier output. They might be thinking of one of two things. One is either they're trying to protect the rectifier from failure, or the other situation that's come up is where they're trying to accomplish AC mitigation. There's induced AC on the pipeline, the rectifier's attached to that pipeline, and it's also connected to a very good grounding bed, the anode bed for the rectifier. They want to shunt the induced AC to the impressed current ground bed. So the question is, would that work? The latter question about AC mitigation, would that work? So the scenario might look like this. We have our rectifier output, and we're going to take a decoupler that has a threshold of several volts, typically plus minus 2 volts or some number in that vicinity, and connect it to cross the output of that rectifier. So again, will that work? Well, it's not likely that that would work. The reason is, what's the output voltage of a rectifier? Typically, it's 10, 20, 50 volts, some number that's significantly more than the threshold voltage of the decoupler. With the rectifier output being above the decoupler threshold, the decoupler is instantly going to turn on. It's going to look like a dead short across the rectifier terminals, and the clearing device, such as a breaker or a fuse, is instantly going to take the rectifier offline. So there's no more CP output from the rectifier. Now, most rectifier settings are going to be above any reasonable decoupler threshold, so this is not likely a solution in any case. Having said that, there have been rare cases where a particular Dairyland product called the ISP has a threshold of about 20 volts, and it has been applied across rectifiers, but it is not recommended because the operation of any decoupler is still, upon reaching the threshold voltage, say during fault or lightning condition or any electrical disturbance, the decoupler will still trigger into the shorted mode and it's going to cause a short across the output of the rectifier, and it's going to still trip the rectifier offline. Some clients have said, well, we can live with that, but we do caution against doing this. This is the one exception to the previous discussion. The last topic we can talk about is when a pipeline has had a mitigation system applied to it, AC mitigation, for an induction from overhead power lines, and the voltage is still too high. So why would the induced voltage be high if a mitigation system has been employed? They wonder, does the decoupler not work? Or is the mitigation system designed poorly, or is it not functioning? So why would you have high voltage values on a pipeline? Well, we can assure you in almost every situation the decoupler is working just fine. And there's ways we can prove that, and we'll have a last slide here to talk about that. However, the basic problem is the resistance of the grounding system is too high. It's not a very effective ground, so no current, or not enough current, flows to the grounding system, and by this we mean AC current flows to the grounding system. So the voltage is not collapsed on this system. And if the voltage is not collapsed, one would say, well, the mitigation system isn't working. Remember that mitigation is by degree. There's more or less voltage on a pipeline based on a number of factors. You could put more grounding material in, that will cost you more money, but it would bring down the voltage. So systems are designed to have a balance between cost and efficiency. More grounding material can go in if, in the case of an unacceptable mitigation system, the voltage is still too high. Additional grounding material or a better grounding system would reduce the voltage on that. So NACE puts the goal at 15 volts, and again, that's a safety concern. We've talked about that earlier in the presentation. That's a level we want to get below. And if you're considering AC corrosion, you want to stay not just below the safety levels, but below the levels that are appropriate for your pipeline, considering soil resistivity and the induced voltage. And that may be down to just single-digit volts. There's different effects on the soil in different seasons. Soil can be wet or dry, depending on the time of year, depending on the season. Dry soil has high resistivity, and a mitigation system will be less effective in dry soil, all things equal. Keep in mind also that the load current on the power company's lines will go up and down, and that will affect the induced voltage that you see. In fact, be very cautious when you take readings. The time of day that you take the reading and the season of the year that you take the reading can greatly affect the reading you get and the results or the assumptions that you make. Time of day and power loads will swing wildly, and seasonally will also vary. And so you really want to trend induced voltage over time and leave a recorder out there to obtain voltage values. Finally, one possibility that should at least be considered is if the decoupler or some type of grounding system that attaches it were severed, that would affect the mitigation system. If a point that had been mitigated is now open-circuited, then the pipeline will rise to the open circuit voltage, basically the unmitigated voltage. One last slide. People will ask how they can know if the decoupler is working. And there are specific tests that can be done just with the decoupler itself as a pass-fail test. However, the simplest test you can perform is one you already do, and that is taking a normal pipe-to-soil voltage reading and determining if that represents a typical or reasonable or normal reading. If the decoupler were conducting or failed shorted, then it would affect the cathodic protection reading. The voltage would be collapsed. So any CP technician could take a pipe-to-soil reading and indirectly know if the decoupler is working. Normal, acceptable CP values represent a decoupler that is functional, because you definitely see it if the decoupler were conducting or shorted. As a comment, it is exceedingly rare for a decoupler to ever be failed, but if it does fail, it would fail shorted for safety. So you'd see that in the readings. And again, there is a separate test just of the decoupler using an ohm meter It's very simple and easy to do, but it does involve taking the decoupler out of the circuit. So that would be talked about separately, and that information is available if you need it. If there are additional questions, if this spurs additional thoughts, feel free to contact us. We take a lot of questions every day from users all over the world, and we're happy to answer those. You can reach me specifically at mike@dairyland.com, and we'd be glad to assist. Thanks for listening.